In this session, we will look at the law of large numbers. There's actually two of them, a strong law and a weak law. So let's start with a little thought experiment. You flip a coin 4 times. The expected number of heads is 2. You get 3. How surprised are you? You're expecting 3, you got 2. Or you're expecting 2, you got 3 rather. It's not too surprising. You flip the coin 400 times. The expected number of heads is 200. You get 3. Not surprised, are you? Well, we begin to suspect that the coin isn't fair and something wrong. Okay, so you flip the coin 400 times. The expected number of heads is 200. We get 225. How surprised are you? Maybe intuitively we expect, yeah, all right, 200, but we don't necessarily expect exactly 200. Okay. We have a sense that the observed mean of values for a large number of trials should be close to the expected value. Okay. So the two laws that we are going to discuss, these justify this intuition. Okay, so the first one is called the weak law of large numbers. So what this says is that you have a sequence, an infinite sequence, x1, x2, and so on, of independent and identically distributed random variables. Okay, so they're all binomial random variables, or they're all independent Poisson random variables with the same parameter lambda. And each having a finite mean, exponential of xi equals mu, and a variance sigma squared. Then for any epsilon greater than 0, the probability of x1 plus x2 up to xn divided by n. So out of this infinite number of random variables, independent and identically distributed, you chose n of them, and then you took the sample mean, right? So you took the sample mean, and then you subtracted off the expectation. So the probability that the sample mean of n of these identical independent random variables, the probability that the difference between that and the expected value is greater than or equal to epsilon, that probability goes to 0 as small n goes to infinity. As you take larger and larger samples, the probability that the sample mean differs from the expectation of random variables, no matter how small you make your epsilon, as you take larger and larger n, the sample mean gets really, really close to the, will get arbitrarily close to the expectation. Okay. Another way of putting it would be let xn with a bar on it and be the average of n independent, identically distributed random variables, each having the same finite expectation mu and the same variance sigma squared. Then for any epsilon greater than 0, the limit as n goes to infinity of the probability of the absolute value of xn minus mu being bigger than epsilon is 0. Another way to look at it would be that this difference, that the probability that the sample mean minus the difference between the sample mean and the expectation, probability of that being less than epsilon is going to go to 1 as n goes to infinity. Okay, so this is one of the big results that then can be proved by the Chebyshev inequality. Since x1, x2 up to xn are independent with the same distribution, we have that the variance of the sum is just sum up all the sigma squares. You're going to get n sigma squared. Then the variance of the sample mean is equal to 1 over n squared, n times sigma squared is equal to sigma squared over n. And for the expectation, we have that the expectation of x1 plus x2 plus xn equals n times mu. So then the expectation of the sample mean is equal to mu. Then by the Chebyshev inequality, the sample, the difference between the sample and the expectation of the sample, take the absolute value of that, is greater than or equal to epsilon. Well, the probability of that is less than or equal to the variance of the xn bar divided by epsilon squared. So we go back to Chebyshev, get this. And now if we put in all our results, we'll get that the difference between xn bar from the expectation, probably of that being greater than or equal to epsilon, is equal to 1 over, is less than or equal to 1 over n sigma squared over epsilon squared. And then as n gets very, very large, this right-hand side is going to go to 0. Okay. Or another way of looking at it is as your sample gets very, very large, the difference between the sample mean and the expectation being less than, the probability of that being less than any given positive epsilon goes to 1. The strong law of large numbers, we call it strong because it implies the weak law, but the weak law doesn't imply the strong law. It says that once again, the strong law as a limit says that, okay, sorry. The weak law as a limit has the limit on the outside. Okay, so here's the sample mean minus mu, take the absolute value of that, the probability of this being less than epsilon as the sample mean gets very, very large is 1. Now, in the strong law, you say the same thing, except you move the limit sign is inside. So you take the sample mean and then you let the sample mean go to infinity, and the probability that that's going to be the expectation is 1. Okay, so the placement of the limit is the difference in the and now if we look at the exact statement of the law for a sequence of identical independently distributed random variables, x1, x2, x3, and so on, with finite expectation mu and a bounded fourth moment. That says that we can put this limit over here. So that's a stronger condition. And so it's possible to construct random variables for which the weak law holds, but the strong law doesn't hold. The proof would be more than we want to do in this course. Okay. So that's the discussion of the strong and weak laws of large numbers.